Okay, this is the fourth presentation in the Energy Work Power series. Make sure that you've watched the first presentation on energy and that there's all different forms of energy. Mechanical, light, chemical, nuclear, what have you. Then the second presentation is on work. That's where we actually see some movement based upon a force being applied. The third presentation is on the work energy theorem that describes the change in kinetic energy specifically is equal to the amount of work being done. And but interesting in that presentation, I didn't mention anything about how fast that change in energy would be done. And that's something that we're going to talk about in this presentation, which is power. So power is a really important concept. We talk about power weightlifting events. We talk about athletes that are powerful. We talk about power in terms of, our light bulbs, or our power in terms of maybe a speaker or a sound system that we get, or power of a car engine, or what have you, horsepower, what have you. All right, so this is a really important concept to dive into, and throughout the semester, we'll probably focus a little bit more in on power. It actually gives us a lot of insight in terms of what's going on mechanically and how a person can go faster or try to sustain an effort over a longer period of time for an endurance event. All right, so let's talk power. We change over to the presentation. All right. Power. The definition of power is the rate at which work is done. It's how fast work is done. And remember, work is a force applied over some distance. That work is independent of time. I could do a certain amount of work. I could do it over a long period of time, or I could do it over a short period of time. Power is how fast we are doing work. So in essence, power describes the rate at which energy is transferred from one object to another. Or another way to say this, and I've used this other word, the rate at which energy is transformed from one form to another. So there's a couple different ways, or a few different ways of looking at power. So work is applying a force over some distance. Power is how fast we are doing work. It's how fast we're applying a force over that distance. All right, how fast we're transforming energy from one form to another, how fast we're transferring energy from one object to another. All those are correct statements, all saying the same thing. I always use the light bulb as an example here for describing power. A light bulb, you go and buy a white light bulb, and you may buy a 60-watt light bulb. That 60-watt light bulb is representing power of the light bulb. It's representing how fast that light bulb is transforming electrical energy to light energy. And if you want a brighter light bulb, you buy a light bulb with more power, a 100-watt light bulb. And a 100-watt light bulb will transform electrical energy faster than a 60-watt light bulb to light energy. Okay, that's the concept of power, and we'll talk about this in the human body in terms of transforming chemical energy to mechanical energy. Okay, so the equation power is work over time. In the linear world, we would do we can replace work with the equation FD. I left out the cosine theta, so here it's implied that F and D are both vectors, and they're in the same direction. Power is a scalar, by the way. I should have put that in the notes, but power is a scalar. Work, energy, and power are all scalars. So FD over delta T, and you should be able to see the velocity in that equation as D over delta T. That's velocity. So power, another equation, is force times velocity. It's how fast a force is being applied. So we really have two equations for power. It's work over time or force times velocity. In the angular world, we would do torque or joint or moment times angular velocity. Torque and moment are the same, mean the same thing. So the angular world, we would do torque times angular velocity. In the linear world, we would do force times velocity. But both of them represent work over time. And power, all forms of power, have units of watts, power stations, what have you. All right, so in the human body and the human performance, because this is ultimately what I'm interested in. So I want to understand how to go faster, how to go further, how to go longer, how to sustain a pace over a longer period of time. Well, what I really want to understand is how to transform chemical energy in the body to mechanical energy. Power represents how fast we can transform that chemical energy to mechanical energy, either aerobically or anaerobically. And so we start using terms like aerobic power and anaerobic power. That describes, those two terms describe how fast we transform carbohydrate aerobically to mechanical energy. Anaerobic power tells us how fast we transform chemical energy to mechanical energy. So what we want to do in a training program is, in essence, train these energy systems depending on what task we're trying to achieve. If I'm trying to do, a strength type of event, like, maybe a lineman on football, or maybe I'm doing a power event, how much I can lift one time. I want to be able to train that anaerobic system to transform chemical energy to mechanical energy as fast as possible. I want to be able to generate a lot of force over a short period of time and move an object. Aerobically, if I'm an endurance athlete, I want to train that aerobic system to transform chemical energy to mechanical energy over a long period of time. So I don't want to engage the anaerobic system much at all during an endurance event in order to go as long as possible. And so I train my aerobic system to be to better convert chemical energy to mechanical energy, and therefore I can run faster and use the energy transformation of chemical energy to mechanical energy versus relying on anaerobic conversion. What a person can do is not limited only by the total amount of energy required, the amount of work done, but also by the rate at which energy can be transformed from one form to another. For example, chemical to mechanical. So the limitation of some tasks is often related to how fast we can transform energy versus how much we can transform. Because I want to win the race. It's not just a matter of trying to complete a distance. I want to complete that distance as fast as possible. And so my human performance is often a function of how fast we can transform energy from one form to another. All right, so now this is where we get a little bit tongue-tied with this, but let's go through this. We often use phrases like energy absorption or energy generated. Remember, conservation of energy cannot be created or destroyed, but it can transform from one form to another. And remember, the work energy theorem is a description of the change in kinetic energy specifically. So let's just go through some of these, and then just to get some of the phrasing down, and then I'll go through and apply it to cycling. I'll talk about swimming as well. So when work is positive, remember, work, energy, and theorem are all scalars. But when work is positive, force and displacement are in the same direction. That means power would be positive because power is how fast work is being done. So if work is positive, power would be positive. That means final kinetic energy is greater than initial kinetic energy. That means we would say, word on the street, energy is being generated. Remember, energy is not changing. The total amount of energy is not different, but we are transforming energy from one form to another, and we are having an increase in kinetic energy. When work is negative, that means force and displacement are in different direction, because work is force times displacement or distance. That means power is negative because power is rate of work being done. Time is always going to be positive. And we say energy is absorbed. That means work energy theorem, the final kinetic energy is less than the initial kinetic energy. All right. Work energy and the work done on the object would cause the object to slow down. So we would say energy is being absorbed. Remember, total energy is the same, but the amount of kinetic energy is less in this case, and therefore we're slowing the object down, for example. All right, so let's look at a schematic. All right, so this is just a simple example of doing a bicep curl exercise, and I've got two plots here. The first plot is position versus time. So on the y-axis is elbow angle. This is anatomical position is 0, and flexion angles are increasing. So we go through flexion here, and then this would be extension. And I'm only showing the flexion part right here. And then down here, I've got angular velocity. Positive angular velocities mean flexion, negative angular velocities meaning extension. So this first example, curling up, would be this first part right here, up to max flexion, and would be where angular velocity ultimately goes back to 0. So we have speeding up and slowing down of the object. Given the torque about the elbow is always positive during this movement, the bicep brachii are always active, trying to cause flexion. Okay, so let's look at this. Power will be positive anywhere in this region. Power will be positive anywhere in this region. Power will be negative anywhere in this region where we go from a flex position down to an extended position. So now the return from this position back to this position. Power will be positive. T equals, T times omega. Torque times angular velocity. Just angular world, angular terms instead of force times velocity. The joint moment will be positive throughout the movement. So that bicep brachii is always trying to flex through flexion and through extension. So this is moving through a controlled extension and not trying to forcibly extend the elbow. So power will be positive here because torque and angular velocity will have the same direction. Power will be negative in this region because the torque acting about the elbow is always going to be positive because the bicep brachii is always trying to flex and causing flexion. It's still trying to flex, but we're going through extension. So I'm still contracting these muscles. Okay. So the torque generated is positive, but the angular velocity is negative. Therefore, they have different directions, and power will be negative in that red region. All right, eccentric contractions will have a negative power since the joint moment is in a different direction than the joint velocity. Okay, eccentric contractions will be negative because I'm trying to flex at the elbow. I'm trying to generate a torque to cause flexion, but I'm going through extension. So I have negative power. Concentric contractions will have positive power. I'm trying to cause flexion and I'm going through flexion. All right. I'm generating power is what we often say, and I'm absorbing power. I'm generating energy. I'm absorbing energy through eccentric contractions. That's how we would word on the street say things like that. Now remember, we don't destroy energy. We can transform it from one form to another. And as we go through eccentric contractions, we're transforming energy from something to something else. And in this case, it would maybe transforming kinetic energy to spring potential energy because we're stretching the elastic tissue in the muscle, and that it's no longer kinetic energy. All right, maximum power that we can generate is accomplished by optimizing force and velocity. We don't typically see max force corresponding with max power, nor do we see max velocity corresponding with max power. Think back to the force velocity relationship. The amount of force a muscle can generate is a function of how fast the muscle is generating, or how fast the muscle is being asked to generate force. And as that speed of contraction increases, the amount of force generated will decrease. Power is the product of force and velocity, and we'll often see a peak power occurring somewhere in the range of velocity capability of a muscle, somewhere usually around about a third of that capacity. But force is not maximized at max power, and contraction velocity is neither minimized nor maximized. Okay, so that's important. Oh, I put the swing here. That's just an example um, of of uh, of transforming energy or transferring energy from one object to another. You're pushing the person on the swing. Um, I'll save this example for another time, but it is an example of transferring energy from one form or from one object to another, and we want to keep the person swinging. And so we not only are trying to apply the right amount of force at the right velocity, but we're also timing the application of the force to the person swinging. Okay. All right, so now let's switch gears to our sports, swimming, biking, and running. And I'll start with cycling power because it's very common for cyclists to be very well versed in the use of power because they have power meters on their bikes and they analyze power during cycling. And we'll talk about this cycling power in more detail when we get to the cycling portion of the semester. So right now I'm just shortcutting to the equation. If we do a kinetic analysis on cycling and we add up all the forces acting on the bike, we're going to get these forces. Now, I'm skipping some steps here. We're going to get the force of the person. We're going to get slope, we're going to force of riding uphill or downhill. We're going to get slope, we're going to get a force due to the air pushing on the person. We're going to get slope of, wow, why am I keep saying slope? We're getting the force of resisting rolling and resisting rolling due to bearings having some friction. We have all these resistance forces and we have some propulsion force. Well, if I take this equation and multiply both sides of the equation by velocity of the cyclist, because I got to keep that equality sign the same, I'm going to get this equation. FP represents the power the biker generates. That's representing how fast we're transforming chemical energy to mechanical energy, conceptually. It's also representing the rate of work being done on the bike by the cyclist. The rate of work being done, W over delta T. So if I just rearrange this equation, I'm going to get this equation right here. My bike velocity is a function of the amount of power the cyclist can generate over all the resistance forces. So if I can generate a lot more power for a given amount of resistance forces, I can go faster. If I can transform chemical energy to mechanical energy faster, I'll be able to bike faster. Now here's another way to go. I can have the same amount of power, I can generate the same amount of power, but I can have lower resistance forces. I can have lower rolling resistance. I could have less drag force on the bike. But so generating the same amount of power, transforming chemical energy to mechanical energy at the same rate, but having lower resistance forces, I'll go faster. This is why a triathlete will use aero bars where they're down in an aerodynamic position because that's not costing anything. That's not doing any physiological work, but I've lowered the resistance forces. And so for a given amount of power I can generate, a given amount of rate of transforming chemical energy to mechanical energy, their given amount of VO2, rate of oxygen consumption, I can go faster. Right. So training, we're trying to train the person to generate more power, but we can also do things mechanically to reduce the resistance forces and go faster. This applies to swimming as well. The swimmer can generate power, and we're trying to swim faster by reducing resistance forces, the drag force of water, or we're trying to increase the propulsion force by increasing drag of the hand. When we get to swimming, you'll see how that works out. So we'll be able to swim faster either by generating more power, training the body to transform chemical energy to mechanical energy aerobically or anaerobically, or reducing resistance forces, having better swim technique. All right, in cycling, we can measure power really easily using a variety of tools, a hub-based system, a crank-based system, or I should have put pedals in here as well. And I'll go through the different power meters that cyclists use. But the cyclist is simply trying to measure the rate of rate of transforming energy from one form to another. That's what they're really trying to do. They don't know that all the time, but that's the concept, that they're trying to understand physiology by measuring mechanics, because the physiological world should match the mechanical world. Okay, power, rate of work being done. Work is force applied over some distance. Power also represents the rate of transforming energy from one form to another. The equation is force times velocity, or work over time. Either of those equations work. And the units, I don't know if I said this before, but the units are watts. Okay, units are watts, Newton meters per second, watts. And I think that's it. Okay, thanks. That completes the series of energy, work, and power, including the work energy theorem. And I hope this has been helpful. Thank you.